Hello everyone, welcome back to our channel. So in the previous video we have seen the RS integral property, right? The two properties we have seen. So today we are going to see the another two properties, and the statement is for any real number C, if f belongs to RS integral alpha on closed interval a comma b, then prove that CF belongs to RS integral alpha on closed interval a comma b. And the second one we need to prove integral a to b CF d alpha is equals to C integral a to b f d alpha. సో ఏదైనా ఒక రియల్ నంబర్ దాన్ని సి అనుకుందాం. అయితే ఎఫ్ అనేది ఆల్రెడీ ఆర్ఎస్ ఇంటిగ్రబుల్ అనమాట ఆన్ క్లోజ్డ్ ఇంటర్వెల్ ఏ కామా బి. సో అప్పుడు ఏం ప్రూవ్ చేయాలి? ఈ రియల్ నంబర్తో కలిపి దిస్ బోత్ సిఎఫ్ బిలాంగ్స్ టు ఆర్ఎస్ ఇంటిగ్రల్ ఆల్ఫా ఆన్ క్లోజ్డ్ ఇంటర్వెల్ ఏ కామా బి అండ్ ఇంటిగ్రల్ ఏ టు బి సిఎఫ్ డి ఆల్ఫా ఈజ్ ఈక్వల్స్ టు సి ఇంటిగ్రల్ ఏ టు బి ఎఫ్ డి ఆల్ఫా. సో ఇక్కడ చూడండి ఫస్ట్ వన్ ప్రూవ్ చేయాల్సింది ఇది కదా. మనకేం తెలుసు యాక్చువల్లీ ఇఫ్ ఎఫ్ బిలాంగ్స్ టు ఆర్ఎస్ ఇంటిగ్రల్ ఆల్ఫా ఆన్ క్లోజ్డ్ ఇంటర్వెల్ ఏ కామా బి అంటే ఏం తెలుసు మనకి? దెర్ ఎగ్జిస్ట్ ఫర్ ఎవ్రీ ఎప్సిలాన్ గ్రేటర్ దాన్ 0 దెర్ ఎగ్జిస్ట్ ఎ పార్టీషన్ పి ఆన్ క్లోజ్డ్ ఇంటర్వెల్ ఏ కామా బి that belongs to u of p of f comma alpha minus l of p comma f comma alpha is less than epsilon. ఇక్కడ మనకి f అంటే ఇక్కడ f ఉంది, ఇక్కడ f ప్లేస్లో ఏముంది? cf ఉంది. సో అప్పుడు ఏం చూపించాలి? ఈ f ప్లేస్లో మనం cfని సబ్స్టిట్యూట్ చేయాలి. అంటే u of p comma cf comma alpha అండ్ మైనస్ l of p comma cf comma alpha లెస్ దాన్ ఎప్సిలాన్ అని చూపిస్తే ఈ ఫస్ట్ అనేది ప్రూవ్ అయిపోతుంది. అండ్ సెకండ్ వన్ ఇక్కడ ఏముంది? ఇంటిగ్రల్ ఏ టు బి సిఎఫ్ డి ఆల్ఫా ఈజ్ ఈక్వల్స్ టు సి ఇంటిగ్రల్ ఏ టు బి ఎఫ్ డి ఆల్ఫా. మనకేం తెలుసు ఆల్రెడీ? ఇఫ్ ఎఫ్ బిలాంగ్స్ టు ఆర్ఎస్ ఇంటిగ్రల్ ఆల్ఫా ఆన్ క్లోజ్డ్ ఇంటర్వెల్ ఏ కామా బి అంటే ఏమన్నట్టు? విచ్ ఇస్ నథింగ్ బట్ ఇంటిగ్రల్ ఏ టు బి ఎఫ్ డి ఆల్ఫా ఈజ్ ఈక్వల్స్ టు ఇంటిగ్రల్ ఏ బార్ టు బి ఎఫ్ డి ఆల్ఫా ఈజ్ ఈక్వల్స్ టు ఇంటిగ్రల్ a to b bar f d alpha. ఇది ఆల్రెడీ మనకు తెలుసు కదా, రైట్? ఇన్ ది ప్లేస్ ఆఫ్ ఎఫ్ వీ హ్యాడ్ cf, రైట్? సో ఇన్ ది ప్లేస్ ఆఫ్ ఎఫ్ జస్ట్ సబ్స్టిట్యూట్ cf హియర్. cf and cf. Hence c is a constant, a real number. We get it outside, which is nothing but c integral a to b f d alpha is equals to integral a bar to b f d alpha, which is equals to c integral a to b bar f d alpha. This is nothing but integral cf integral a to b cf d alpha, right? If we shown this one, then the second one will also be proved. Now do you have understood what is the theorem statement and what we need to prove? And now we will see how to write the proof. First we need to write the given part. What is the given part? Then we need to start writing the proof. Start solving the proof. First given for any real number c, which is nothing but c belongs to real number. C belongs to real number and f belongs to r of alpha on closed interval a comma b. F belongs to r of alpha on closed interval a comma b. And now we need to prove this both. So we need to write prove cf belongs to r of alpha on closed interval a comma b, and the second one is integral a to b cf d alpha is equals to c outside integral a to b f d alpha. And now just now only we seen that in order to prove this one, this first one, it is enough to prove that for every epsilon greater than 0 there exists a partition P on closed interval a comma b belongs to u of p comma cf comma alpha minus l of p comma cf comma alpha is less than epsilon. Okay. Here that given is C belongs to real number, which is nothing but C can be greater than 0, C can be less than 0 and C can be is equals to 0. C అనేది రియల్ నెంబర్ అన్నప్పుడు C అనేది 0 కంటే పెద్దది ఉండొచ్చు, C అనేది 0 కంటే చిన్నది ఉండొచ్చు, లేదంటే ఈక్వల్స్ టు 0 కూడా ఉండొచ్చు. సో ఈ 3 కేసెస్ కన్సిడర్ చేద్దాం. ఫస్ట్ కేస్ when C is greater than 0. First case when C is greater than 0 for every epsilon by C. ఇక్కడ ఓన్లీ మనం ఇంతకుముందు ఎప్సిలాన్ అనుకున్నాం, ఇక్కడ రియల్ నెంబర్ C అంటున్నాం కాబట్టి ఎప్సిలాన్ బై C తీసుకున్నాను అనమాట. అండ్ హియర్ C is greater than 0. సో epsilon by C greater than 0, there exists a partition P on closed interval a comma b such that u of p comma f comma alpha minus L of p comma f comma alpha is less than epsilon by C. Okay, and when C greater than 0, we have a note point. When C greater than 0, we have u of p comma cf comma alpha is equals to C of u comma u into p comma f comma alpha, and L of p comma cf comma alpha is equals to C of L comma p comma f comma alpha. Right? Now take these two equations and consider u of p comma cf comma alpha minus L of p comma cf comma alpha is equals to, we got u of p comma cf comma alpha is C into u of p comma f comma alpha. So substitute here cu of p comma f comma alpha minus C of L of p comma f comma alpha, and from these we can take common C. So C is outside and u of p comma f comma alpha minus L of p comma f comma alpha. And we already know that u of p comma f comma alpha minus L of p comma f comma alpha, which is nothing but less than epsilon by C. So less than or equals to epsilon by C, and we have C here, and if we can cancel this C and this C, we get u of p comma cf comma alpha minus L of p comma cf comma alpha is less than epsilon when C greater than 0, which is nothing but f belongs to cf belongs to, in the place of f we have cf, so cf belongs to R of alpha on closed interval a comma b. Now let us consider what will be the case if C less than 0. If C less than 0, which is nothing but minus C greater than 0, which is nothing but for every epsilon by minus C greater than 0, there exists a partition P on closed interval a comma b such that u of p comma f comma alpha minus L of p comma f comma alpha is less than epsilon by minus C. And remember this term which is can be further used, and when C less than 0, we have u of p comma cf comma alpha is equals to, when greater than 0, we have these conditions, right? When less than 0, the upper RS sum will be like this. C will be outside. Here we get L. In the above statement we got U only. But here we will get L. Please do remember this one. And P of P comma F comma alpha. And L of P comma CF comma alpha is equals to C. Here it is L, has C less than 0, we get U. U of P comma F comma alpha. And now consider U of P comma CF comma alpha minus L of P comma CF comma alpha is equals to CL P comma F comma alpha minus Cu P comma F comma alpha. Okay, now take common minus C, which is U comma P comma F comma alpha minus L of P comma F comma alpha. Minus C into U minus Cu, minus into minus plus C into U plus Cl P comma F comma alpha. So from this we can say that just now we got U of P comma F comma alpha minus L of P comma F comma alpha is less than epsilon by minus C when C less than 0. So we can substitute epsilon by minus C here. So less than or equals to epsilon by minus C here, and we have minus C term, therefore minus C, and we can easily cancel this minus C and this minus C. We have less than epsilon, which is nothing but U of P comma CF comma alpha minus L of P comma CF comma alpha is less than epsilon, which is nothing but, in the place of F we have CF, so CF belongs to RS integral alpha on closed interval a comma b. And now we have seen the two cases, when C greater than 0 and C less than 0. Now we need to see C is equals to 0. When C is equals to 0, CF, which is nothing but, we need to multiply 0 into something which is equals to 0. Right? If C is equals to 0 belongs to real numbers, then these also belongs to real numbers, which is nothing but, hence for every or all C belongs to real numbers, F belongs to RS integral alpha on closed interval a comma b. Okay? CF, sorry. In the place of F we have CF. CF belongs to RS integral alpha on closed interval a comma b. Now let us prove the second one. And we prove that in the first case CF belongs to RS integral alpha on closed interval a comma b. If CF belongs to RS integral alpha on closed interval a comma b, then which is nothing but integral a to b CF d alpha is equals to integral a to b bar CF d alpha is equals to integral a bar to b CF d alpha, right? And now consider this first two terms, which is integral a to b CF d alpha, which is equals to integral a to b bar CF d alpha. And what do you know? Integral a to b bar f d alpha is nothing but, this is upper RS sum, which is nothing but u of p comma f comma alpha infimum of, this is infimum, right? Upper RS sum, upper RS integral, sorry, this is not sum, this is integral, where p is partition on closed interval a comma b. This is what we know, right? Now, which is nothing but, this term is nothing but infimum of C of u of p comma f comma alpha, where p is partition on closed interval a comma b. And if you consider the supremum, which is nothing but supremum, when c greater than 0 only, you will get the infimum, which is upper RS integral. And supremum C L p comma f comma alpha, where p is a partition on closed interval a comma b, when c is less than 0. When c less than 0, you get the lower RS integral. When c greater than 0, you get upper RS integral and infimum. Here, the supremum. This can be written as integral. Infimum you have, so a to b bar c of d alpha, when c greater than 0. And this can be written as integral a bar to b c of d alpha, when c less than 0. And this can be written as we know, integral a to b c of d alpha is equals to integral a to b bar c of d alpha is equals to integral a bar to b c of d alpha. This can be written as integral a to b c of d alpha, when c greater than 0, and integral a to b c of d alpha, when c less than 0, which is nothing but integral a to b c of d alpha is equals to, c is a real number and a constant, so we can take outside the integral, which is c integral a to b f d alpha. Hence proved. This is how we prove. And if you have any doubt, please do comment in the comment box and like to my video. Thank you all. Happy learning to you. And if any of the person are new to my channel, please do subscribe it.